Hello guys, in last lecture we talked about radioactive decay. We mainly focused on alpha, beta and the gamma decay. We know that when the nucleus becomes unstable or if there is a weak nuclear force, then we expect to have radioactive decay. And in today's topic, the half-life is related with the radioactive decay process. The half-life is the time in which half of the original amount, okay, keep in mind this, half of the original number of nuclei decay. So that means if you have 100, right, and if you go to half of it, which is 50, the time that it takes is called the half-life for that particular substance or that nuclei. Another analogy, let's say you got a candle, right? Okay, there is a candle right here. Okay, now what's going to happen is over time the candle, the amount going to decrease. Let's say over time the amount of the candle left over is, let's say, the half of the amount is like this, okay, like this much. Let's say initially we have this much, right, and after like certain time it is half of the original candle, right, and the time that it takes, okay, the time that it takes to become that half of that original amount is called the half-life. However you want to think, that's the definition of half-life. It might not be well appropriate to just talk about candle here because we have to think about the radioactive decay, how elements go through that decay process. And we all talking about that nucleus, right? There's a nucleus, right? And there's a nucleons, right? Those protons and the neutrons, that how they go through this the decay process. And the decay process can be alpha, beta or gamma. Okay, if you want to know more about it, you can go to the previous lecture and learn about that. If you look at this graph, what do you see? What kind of graph is this? This is an exponential graph, right? This is an exponential graph. So if this is exponential graph, then we do not expect the linear drop like that, right? We do not expect that. And that's pretty important concept. When you're talking about half-life, we're talking about exponential decay, right? Initially, we have 1,000, right? 1,000 times, here's the unit 10 to the power 3, right? That kind of thing, but it doesn't matter. Let's say we have 1,000 initially, right? Then we go up, here is a 0, right? All the way down here. So if you go half of it, it's going to be 500. Then if you drag this one and all the way go down here, this is T1 half. That is half-life for this particular nuclei, let's say, right? Or that particular substance. You know, we don't know it is a substance or nucleons, but here in the axis it says nucleoids, so it's a nucleoid. So the half-life is this much, like T half-life is here, and the T half-life is given on the table here also. So the initially we had this much, and and we got this much, half of that, right? Half of that is the half-life. Now, if you go again the second half-life, right? Then you again deduct like half of that that amount from this amount. You deduct that and you divide that. That is a second half-life, and third half-life, fourth half-life, fifth half-lives. So these are called number of half-lives. Okay, so how many number of half-lives here? So okay, here is a 0 half-lives, right? And you just all the way down there, right? You increase that. Those are called number of half-lives, and that's pretty important concept here. Okay, these are the equations that we encounter when you talk about half-life, but these are pretty difficult equations, and you know, we don't want to use calculator during MCAT, and we don't want to like make our life very difficult. But these equations are here to just like get to know the relationship between the initial amount and the final amount, half-life and the initial amount, and those type of thing. Again, NFT is the quantity of the substance that remains after a certain time. NF naught is the initial amount, right? And you have to use a logic. If something is initial is more, that means final should be less. And okay, during the calculation, if you get the final more than the initial, then that's wrong. You did something wrong. Okay, very important concept. And T is the time elapsed, and T 1/2 is the half-life of the substance that we're talking about. Okay, and there is another equation like this one, right? T 1/2 is the half-life for a particular substance is equal to lnf2 divided by this kind of wavelength kind of symbol here, right? And this is called a decay constant. Okay, and again, what is decay constant? You don't need to know it, but what it's going to tell you is how quickly the nuclei, or how quickly the total number of nuclei will decrease. Okay, this is going to give you that kind of information. Again, decay constant is specific to the type of decay and the isotope being studied. What I mean by type of decay, it can be alpha, beta, or gamma. Okay, and type of isotope, you know what is isotope is, right? And there are different types of different means like different elements that involve in that kind of that decaying process. Okay, yeah, but don't worry about this one. So we're gonna do like very easy problems in just a moment, which will explain in greater detail. Okay, as you look at here, right, what you see is there is a iodine 131, and here what we're doing is we targeting thyroid gland. So what to simplify this thing, so we usually use this radioactive isotope to as a therapeutic or diagnostic purposes. In this case, iodine 131 is used for the treatment of hyperthyroidism. Okay, what's going to happen is once you take it, right, what's going to happen is your medicine, or what I don't want to say it's a medicine, or this isotope in the form of pill is going to go to your small intestine, absorb to the bloodstream, right, and it's going to concentrate it into the thyroid gland, and it will target and destroy the gland cells, which are bad cells, or think about that way. And also this is widely used in the thyroid cancer also. So that's why decay, the radioactive decay, is pretty important, and it tells you and it gives you an idea about how we can target certain things, and it can be beneficial as a therapeutic or diagnostic area. Okay, and that's pretty important here, and nothing other than that. You don't need to know anything about this. Okay, but remember this, now this is a decay process, right, and it releases some kind of radiation or energy or particle, and those type of things you need to be aware of. Okay, let's do some practice here. So there is a drug X, right, which has the initial amount of NF naught 80 gram, and is 10 gram, which is after time t, which is 8 hours in this case, and we need to figure out the half-life of that drug X. Before I solve this problem, I want to give you some equations that will be very beneficial, or you're going to love these equations. So when you divide n over n naught, is basically going to tell you the fraction that remains, or fraction remaining, okay, which is going to equal to 1 over 2 the power n. Okay, and again, this is pretty important equation, you need to know it. And another equation you need to know is time t equals n times t 1/2. So what does that mean? What is n though actually? N is the number of half-lives elapsed. So this is a number of half-lives elapsed. Okay, let's solve the first question here. So if you divide n over n naught, that's going to give you a fraction remaining, right? So that means in case of here, right? Let me use the different color. That's going to make you look this one big, pretty one, right? So what's going to happen? What is the n? 10 over 80 is the n naught, which is equal to 1 over 2n. That means 0, 0 goes, right? 1 over 2 to the power 3 equals 1 to the power n. Again, this is n, you have to put on top, right? It's not like multiplying with 2, okay? That's pretty important concept here also. So that means n equals 3, right? That means that's the number of half-lives elapsed. To find out the t1/2, we have the equation here, right? So what you have to do is you just like divide time by that number of half-lives. So that means t1/2 gonna give you 8 over 3, right? And which is pretty, I think 2.6, almost like that. You can estimate that. You don't need to be like exact, but just estimate it. Okay, the question number 2, an isotope with half-life of 4 hours, what percentage will be left after 16 hours? Okay, this deals with percentage, and again, during the exam, if you see the percentage written, okay, the method I'm going to show you, that's going to be very useful. Okay, so what you actually have to do is this. Okay, let me do this. Okay, so what you have to do is just write down one by one. Let's say you have in first column, just there's a half-lives, write down half-lives. Okay, then in the second, write down time. Okay, in this case we have in hour, right? And the final one, write down percent left. Okay, percent left. So remember that we have given the t and we have given t1/2. So that means we can determine n, right? Which is basically means 16 over 4. And again, this is here, right? The equation that you use that and you just get the answer. So that means it is 4. There are 4 like number of half-lives. That means we start from 0, 1, 2, 3, 4, right? Now the time is we have to go up to what? 16 hours. So it should be 16 hours. We know that, right? And it has to increase in the 4, right? The 4 increment, right? So if you have initially we have a 0, then 4, then 8, then 12, then 16, right? Now percent left. Initially we have 100%, right? Nothing decayed. Then we're going to have to 50%. Okay, then we have a 25%, then 12.5%, then finally we have 6.25%. So that means 6.25% will be left after 16 hours. And if you use this method, it's going to be easy for you to understand. Okay, and the question number 3, again, it's the same idea here, right? You need to find the t. So to do that, you have n and n not given. You can get the fraction remaining, right? So what does that mean? You just divide 25 over 100 like that way, right? And you just do this, and it's going to be 1 over 4, right? And 1 over 2n, and the n gonna be 2, right? Because 4 is to the power 2, right? That's why. So that's what you know, right? So if you got n equals 2, then you can find t, right? Basically, you do just 2 times t/2 is what? 36, which is going to give you 72 hours. What does that mean? After 72 hours, right, the 100 gram, okay, 100 gram, after 72 hours, only 25 grams were left. Okay, that's what it's telling you. Okay, and the question number 4 is just like more like conceptual. Okay, so you have a carbon 14 has a half-life of this much, right, years, right? And what does it mean actually? Okay, if it has half-life that, what does that mean? So we know that, let's say you started with 200 grams of, let's say, carbon 14. So the carbon 14 undergoes this beta minus decay, okay, and the identity got changed, right? Carbon to nitrogen. And you need to recall that when there is a beta minus decay, that means you adding 1 to this atomic number, which is carbon. If you add 1 to the atomic number of carbon, which is 6, and 6 plus 1 going to give you 7, which is the atomic number for nitrogen, right? So let's say you started at 200 gram, right? After 5730 years, right, how much carbon are you going to have? 100 gram, right? Because half of that will decrease, right? Half of it will be 100 gram. But you can say in other way also, but how much nitrogen will you produce though? Half, like 100 gram, right? So 100 gram and 100 gram. Okay, that's in the first half-life. Let's say we go to the second half-life. That means 2 times this 5730, whatever the number gonna be. If you go to that number, now you have 100 gram at the half-life of 5730, right? If you go like second half-life, that's 100 gram will again decrease to the 50 gram. But what about the nitrogen though? Nitrogen, you add 50 to the nitrogen, that's going to give you 150 gram. So at the second half-life, right, lives, so what you're going to have is you're going to have 150 gram of nitrogen. Okay, whatever I said, that's everything right here. Whatever I said is everything right here. Okay, you can just like work on it or look at it and just go back and see what I'm talking about in previous slide. Okay, so finally, before I end today's lecture, I would like to give you some information regarding half-life, the importance of the half-life. Okay, let's say I'm gonna say you're gonna be a physician in the future, right? So you are a physician, okay, physician. Okay, now there is a patient coming to see you, right? And he has active TB, okay, or tuberculosis. Okay, so now you have to prescribe him. Let's say usually they prescribe isoniazid. Okay, you have to prescribe him isoniazid. Now, does it matter? Do you need to consider half-life of isoniazid? Okay, the answer is yes. Okay, and why you need to consider that is very important thing to note. Again, remember, drug half-life is basically means time required to reduce the plasma concentration to 50% of its original value. Let's say isoniazid was, let's say 300 milligram, let's say 300 milligram, right? And if there is a plasma concentration right here, you just took intake it. Now the plasma concentration is some amount, right? And the half-life will tell you at what time the plasma concentration will be 50% of that amount you take. Okay, so that's pretty important, right? So it's gonna give you the information how long a drug will remain in the body. And why is that important? So usually the physician prescribe isoniazid 300 mg, and you have to take 1 pill or 1 tablet per day, right? Why they don't give you 2 per day? 2 per day? Why they don't do that? Because think about this way, okay? Again, the half-life of isoniazid is 1 to 4 hours. If you are a healthy person, your liver is working nicely, your your kidney is working nicely, because kidney has a role in excretion of those metabolites after the drug gets metabolized, type of thing, right? And again, the half-life is usually 1 to 4 hours. But if your kidney is working nicely, your liver is working properly, then the system, right, or your excretory system, like 50 to 70% of a dose of isoniazid will excreted from the kidney in 24 hours. So that means up to 24 hours, you're going to feel like you have isoniazid in your body. So that means if you give 300 mg within, like, let's say 10-hour period, right, per day is 24 hours, right? If you get 2 pills at the same day, now you're adding 300 mg plus you adding another dose of 300, that's overdose. So you want to kill that patient? No. So that's why you need to understand the half-life, right? You need to know how long this drug will stay in the body. And that's very important thing to note. And that's why the physicians should be careful about prescribing drugs, and you don't want to overdose the patient, right? And you need to know the dosing interval, and to determine the dosing interval you need to know the half-life of the drug that you gonna prescribe. And this is just the biological aspect, you don't need to know about it. But finally, what I want to tell you is, if you know these equations, like these equations right here, right, then you will be okay in any kind of problem in MCAT. All right, thank you so much for watching. Bye bye.